guys, this is Chris here, and I'm bringing another Advent of Code video to you, day 20, pulse propagation. Right out the gate, I'll just kind of say that this particular problem gave me a couple of challenges that made me take a little bit longer on it than I normally would. I did want to finish the challenge, so rather than providing a video for you of the process I went through, I'm just going to provide a video of the problem and then the solution. So to keep things short, I won't read through the entire series or story rather. I've looked at this for far too long, and honestly, I'm over it. But you know what? I learned something. I took a path. That path ended up biting me in the long run. I had to redo some things. Still not fully satisfied with my solution, but I do have a solution. And with a little bit more rework, it would be a great solution. So let's talk about part one. Part one essentially gives a set of input that is defined like this. And you have three types. You have broadcaster, which there's only one of them per input. You have flip-flop modules, and then you have conjunction modules. The flip-flop modules work in such a way that they're either on or off. They're initially off. And if they receive a high pulse, it's ignored. But if they receive a low pulse, it flips the state. And if it turns it on, then it sends a high pulse. And if it was on, it turns it off and sends a low pulse. So it only does something if it gets a low pulse. All high pulses are ignored. Conjunctions, on the other hand, remember the states of the inputs that are provided to it. And if you send it a low pulse, it'll remember that state. And if you send it a high pulse, it'll remember that state. Regardless of what gets sent to it, it always sends a pulse. It will either be a high pulse or a low pulse. It's always a high pulse by default and only a low pulse if all of the inputs it remembers are high. Now, there's one thing I did out of the gate that I was happy about, which is I made sure that I did some inspection and got everything that could communicate with it ahead of time, so I knew how to properly associate low and high pulses. What I mean is there might be 10 inputs, but you may only have one or two things sending to it initially. So you want to make sure you have those initial states. There is a single broadcast module. That's the input. When it receives a pulse, it sends the same pulse to all of its destination modules. Essentially, when you press the button, it always sends a low pulse. So the idea here is that you want to receive the initial pulse on broadcaster and then pulse out or signal A, B, and C. And then A, B, and C are flip-flop modules. They're also going to signal out. A is going to signal B, B is going to signal C, C is going to signal I and V. The one thing to keep in mind is that you have to process them in order, so that if broadcaster says signal A, B, C, A, B, and C should process before B processes. In other words, we're not going to start with A, process A, then do B, B, C, C inventory. Or I and V. We're not going to do that. We're going to process A, B, and C, and then B, C, I and V, A, etc. So that's one other caveat, which means we need some sort of queuing mechanism. I was pretty quick to pick up on that as well. What really where my folly was is that I decided to create all of these as modules. And actually, that's probably not a bad idea, but create a module interface and then the implementation of a broadcasters, flip-flops, and this third one, conjunctions, would be buried in those details that we'd use an interface. And that worked out okay, but the way I implemented the way signals were sent and received kind of hindered my progress, and I had to do things a little bit hacky, but we'll get to that. So here's some examples. We're not going to dive into that. Here's some more examples. We get a second set of input. The one thing I'll mention here is on the second set of input, this output is not defined on the left side. So it's considered just a test module. So that's just something you need to prepare for. Initially, I said if there's something defined on the right side, a quote-unquote destination, and we haven't defined it as a module, then error. And when I got to the second test example, I found out quickly that I needed that. So I also created a base case. So here's what happens when you push the button. Here's another example. We're not going to go through that. But the end result is we needed to collect the pulses, whether they're low or high pulses, count the values, and then based on those counts, multiply them together to get a total. So this is our first total of the test. And then, as you can see here, I solved the first puzzle. So let's dive in. We'll look at solution 1, and then we'll talk about that implementation. Right. So day 20, we split this into 2 parts. I did use 2 parts, and I created a module queue. Didn't really see a DQ object inside Go. Maybe I just couldn't find it. If there is one, leave a comment below. I'm here to learn just as much as you are, so maybe there's another approach. This isn't great because of allocation of memory, allocating and deallocating memory, but it works for the use case that I needed, which was just to have a slice that we're always appending and popping from. I could have done the inline in code, but it made things ugly, so I went ahead and just created a type specifically for it, which is a slice of my module interface. We can look at the module interface real quick. This grew over time, but we have a name, we have a signal, we have a pulse, add destination, destinations, add source, will send. Some mixed cases here with upper and lowercase. They really should all be upper at this point, but again, I'm over it, so we're moving on. We can push things onto the module queue. We can pop things off. Pretty straightforward queuing mechanisms. And we have this notify structs. This is how I was able to count high and low pulses, essentially. I decided to go with a Boolean. Maybe an integer would be better, but the case is if it was high, it was true. If it was low, it'd be false. So how do we accomplish this? I used a channel for the high and low sending, and I instantiated this channel, and I looped through, and I parsed the objects, and I decided to loop through twice, once for the initial modules, once for the association. And when I created the modules, I would attach the notify channel to them, so they all had access to that channel. Okay, cool. Kind of doing some object-oriented stuff here using an interface, some interesting things inside of Go worth taking a look at. If you'd like me to dive in deeper into interfaces and channels, I can do that in a different video. Create a Go func to monitor that channel, and we're going to run on that until we close. We close below. We'll look at that in a second. Sorry, let's look at our part 1 solution, not our part 2. Right. So the first problem was we have to push the button 1,000 times, and as many ever lows and highs are sent, that's what we catalog. So I think this solution was fine. We went through, pushed it 1,000 times, everything was sent. Once we're done pushing the button, we close the channel, and that's how we exit out of this code. Not necessary. I did use a wait group because I always like to make sure my code is fully closed out before I proceed. There's some other ways we could have handled this. This is fine. We could have ran this inside a Go routine instead, and then had the range of the notifier in our main loop. That also would have worked. Either way, I digress. This is fine. And maybe that would be a cleaner solution. But we times the low by the high. That gets our first score. In my case, that was a total of this. So remember, that's not how many iterations. That's the multiplicative of the two values. So 666 million. Oh, the mark of the beast. Anyway, what's our second problem? Our second problem was to push the button as many times. Let's look at the actual text. It's really simple. Push the button as many times as it is for Rx to receive a low pulse signal sent to it. Of course, I tried this, and remember, this is straight. This here is multiplicative, so it seems like you made a lot of progress, but really it's lows times highs. In this particular answer, much different in the sense that it's physical, or not physical, but it's actual button pushes. So it's every iteration that it takes to get through. So of course I started mine up and let it run, and it ran for, I don't know, about 10 seconds. And I already decided that it wasn't going to be too slow. And I knew at day 20, it wouldn't be just as simple as, loop until you meet some condition. Mind you, I did go through some trial and error here. So I don't want to make it sound simpler than it is, but at the end of the day, it makes sense. So this is still in place, although really not needed. We could remove it, but because I've already implemented the channels into my other sets of code, it would block if we didn't read, and that gets into a whole nother channel specific problem. Let's talk about the triggering modules. So if you look at the let's look at the input data, because that's what I eventually, after some trial and error, some thinking, this is where I got to. If you look at your input data, you have an Rx. There's only one Rx. So we've got Rx, and if we look at our input, that's fed by df. And that is a conjunction module. So if we look at the rules, we look at a conjunction, because remember, we're looking to see when a low pulse is received. A conjunction is only low if all of the things feeding it are high. So if we go back to our input, if we look at df, it's got 4 things that feed it. Also all conjunction modules as well, but that's not particularly a problem. So we'll go ahead and denote them as, we'll just know that they're all conjunction modules. So let's go back to our main problem here. So we've got, let's list them out. We've got XL, we've got LN, we've got XP, and we've got GP. So these all have to be in the same state. Specifically, so we need it to send high pulse for all of these inputs in order for df. So this needs to be high, this needs to be high, this needs to be high, and this needs to be high for this to be low, to send a low, so that this receives a low. Okay? So this kind of tells us something, because this means that it is possible that we have to go through every single permutation to get to a point where this is all eventually high. But we may be able to take a shortcut here. And so how do we take a shortcut? Well, we know, because of the binary nature, that it is likely that each of these are going to happen in some sort of cycle, meaning that every X iterations this is going to be high, and this is going to be high, and every X iterations this is going to be high, and this number is going to vary for every single one of these numbers. If we can see the pattern, this just becomes a cycle problem. So we need to figure out what cycle each of these are in. And so if we know that this one happens every 10, and this one happens every 500, and this one happens every 6,000, and this one happens every, I don't know, 1,300, what is the LCM, or I'm sorry, the least common multiplier? So we did least common multiplier in lesson 8, or in Advent of Code day 8. Although some argued that we shouldn't be able to use it. You could argue the same here. It may or may not be a least common multiplier answer, but a least common multiplier can potentially get you to an answer at some point in the future. And it honestly should get you to the answer, assuming that if our answer is 6 trillion, that it doesn't take 6 trillion cycles for, let's say, GP to get to that value. So that's how we solve this problem. So that took me a little bit to figure out, but once I figured that out, the implementation was pretty straightforward. So what that meant was I had to throw away essentially some of the old adages that I had in place, and I had to figure out what the trigger modules were. And then from the trigger modules, I had to figure out, so the trigger module in its base case is DF, right? DF is the first triggering module, but we still only reduce the problem to a single entity having to be in a certain state. So in order to speed this up, we back up one whole level. Now, we could maybe go back another level, but I don't think it's necessary in this case. We reduced the problem enough to where we would know by a great magnitude, it is I don't know what's factorial 4, but so that's what we did. So this is what this first loop does. It just gets the trigger modules, and then for each triggering module, it gets it sets up the cycles, and then from the cycles, what we do on each button press is we check, hey, have we set that module in the cycle yet? And if the value is 0, meaning we haven't seen it before, then we just ask, hey, will it send? I was not very happy with this, but this was how I could inject and understand whether or not it's going to actually send a value, and that has to do with the way I structured it as interfaces and modules. And anyway, I digress. So we record the cycle and the button press. So we just need the initial cycle. Now, if we want to be more accurate, we may actually, it might behoove us to go through and say, okay, is there a pattern of cycle? And only if we see that cycle number after X iterations, then we know that that cycle is true. I just went for broke and said, let's just see if it works on the first set, and it did. And so we went with that. Once we have all the cycles found, so we want to check that we know we're done. So we iterate through all the cycles and see if there's 0. And if there is one that's 0, we continue, and we haven't found the cycle, but otherwise we break outer. And then finally, we just continue the same destination push that we did previously. Close the channel, and then at the very end, we loop through our cycle counts, and we get the LCM. So in my case, if we look at the answer, it's extremely high. What is this? We're in the thousands. We're in the thousands, millions, billions, 253 trillion button presses. I mean, sure, maybe we would have eventually got there without doing the cycle checks. I don't know how many my computations were per button press, how long it was taking, and how many button presses I was getting through a second. But it would have taken quite a long time to get to 253. In fact, I think I let it run for at least 10 minutes, maybe 15, while I was working on the solution, the optimized solution. Most of my time on this problem was spent in part 1. I had a lot of distractions, a lot of disruptions, and took myself down a path that just ended up with more pain. But sometimes that's the way it goes. And again, I think that's the beauty of Advent of Code. It's beauty of tackling these kind of problems and these puzzles. We're pushing ourselves to a place that we've never been before, beyond what we think is normal as far as our ability. And we're attempting something that is going to show us how to be a better developer, how to be a better programmer, when we run a software engineer. When we run into those issues in the future, we know how to solve them. They're easy. They're not hard anymore because we know the solution, we know the shortcuts, or at least we have an idea of the solution and the shortcuts. We know the things to do and the things not to do. But as always, that's all I have for today. Over and out.